Welcome back. In our first video, we talked about the shortcomings we face with current approaches to developing software. It's expensive, error-prone, takes too long, and rarely does what it should. In this video, we will introduce you to a much better approach to specifying software. It will enable the computer to write code. Once you see it, you'll never want to go back. We will show you specifications that are visual, intuitive, and easy to use, require no logic, and can be built by a non-techie. This approach overcomes all of the major shortcomings that we currently see with software specifications. Here's how we'll do it. Instead of starting with the inputs and specifying how to do it by stepping forward through an algorithm, we'll invert this process by specifying what every single output of a program is and work inward until they have been fully specified. You want a highest common factor? Then just say it, and say what the two numbers are. Don't start talking about Euclid and iterative loops and initialization of variables. One of those two numbers came from somewhere else? Say where. Keep going all the way down to the most granular level. Let's look at some simple examples. Here we see representations of a ratio and a highest common factor. It's pretty obvious what you need in order to fully specify each of them. Now let's look at something a little more interesting. Suppose we're interested in the nth largest value of an array of numbers. Here we need to specify the array of numbers as well as n. How might we specify those parameters? Perhaps the array is already known and can be hard-coded, like this. But suppose instead the array of numbers is to be specified in terms of something else. For example, it might be defined as the array consisting of the third highest value of each column in a certain table. So we want something like this. In a similar way, n might be hard-coded as 2, or instead might be specified in some other way, such as the highest common factor of two integers that we just saw. Perhaps one of those integers is in turn specified in terms of something else. For example, the number of hours in an overnight flight that crosses several time zones, or perhaps the number of years of life expectancy for a 40-year-old female smoker. As you can imagine, the logic required to implement even this one simple example is far from trivial. Note that we've shown none of the internal variables or looping or sorting algorithms. We are concerned here only with specifying the problem, nothing more and nothing less. You can see that we've used arrows to signify which component is used to specify which attribute. It looks a little better if we use a series of exploding boxes. At every level of detail, we have to explode a component a little further. This works, but it can quickly get out of control. And if you wanted any of these items to be rounded, it gets even messier. Clearly, a two-dimensional representation works only for the simplest of applications. So now, let's take a look at a working model that deals with this in a much better way. It uses a type of 3D visual components that can be opened and closed. It will allow you to specify software of enormous complexity. A special visual editing tool lets you connect these components. Here we can see examples of several of these components that we call inverts. Among them are the highest common factor, ratio, and nth highest value that we just discussed. The first thing you'll notice is how simple they all are. As we'll soon see, inverts have some very powerful properties that can be connected in unusual ways to represent highly complex ideas. An invert may have one or more attributes that are required in order to fully specify it. The attributes for the ratio are naturally called the numerator and the denominator. The inverts that you see here are simply empty templates, since their attributes are not yet specified. Later on, you'll see some much more complex inverts. Let's take a closer look at the different ways in which we can specify an attribute. In many cases, an attribute would be represented with a basic data type, like a number, text, boolean, date, time, or perhaps an array of numbers. In such cases, you can simply hard-code them. These next examples show how an attribute can also be specified using another invert. It's identified here by the bold blue labels in the attribute. You'll notice here in the second example that we cannot see the attributes of the sum plus 3 invert. But using the mouse or keyboard, we can easily open them up so that the attributes are now exposed. Just as easily, we can close it back up again. As we will see, This ability to hide details goes a long way to helping us manage complexity. There is a third way to specify an attribute, and that is by reference to some other invert elsewhere in an invert structure. Here's an artificial example showing how it works. The power attribute of the exponent in quantity 2 is set equal to the divisor of the remainder. When the power number is highlighted, its reference is also highlighted with a green border. You can see that this invert structure goes 3 levels deep. There is no limit on how deep you can go in specifying an invert structure. Simple colour coding of the labels, their backgrounds, and the borders can convey useful information about an attribute. If you look closely at the if reverse attribute of the sorted set invert, you can see that its label is shown in grey italics. This indicates that it is optional and therefore does not need to be specified. Let's select a few attributes in turn. When we select an attribute, its border colour changes to red or yellow. This tells you at a glance whether the attribute has been fully specified or is still incomplete. By now, I'm sure you have a few questions. How many different kinds of inverts do you need? We've created well over 1,000 types of inverts and organised them into libraries. And for most categories, we found that the number of invert templates that you need is actually quite finite. And these inverts already are sufficient to cover a broad range of technical topics. We continue to build and test new libraries. Here we can see lists of inverts from several of the libraries. And here we see various statistical summaries against a collection of numbers. You'll notice the double border that signifies a set, but more on sets later. These 50 date inverts can be combined to represent even the most complex date construct. As an example of how these can be combined, this one shows the next day after the third Friday starting on March 1st, 2024. Since we have asked it to include today, and it is a Friday, this represents the 16th of March 2024. And with another 70 inverts covering times, timestamps and periods, you can easily handle such wrinkles as time zones, daylight savings time, leap years, and public holidays, with everything, all the way down to the nanosecond. Inverts can also cover more complex concepts. For example, this list of inverts represents arrays that are derived from columns of a numerical table. Here you see the invert we met before, for an array that represents the nth highest value of each column in a table. We found that around 150 inverts are sufficient to cover arrays, sequences, tables, and various numerical structures. As another example, here is a list of inverts representing a broad range of statistical measures. These are more than enough, even for the most demanding statistician. Wouldn't you need a lot of inverts to specify a software program? Not as many as you might think. Remember, inverts do not contain low-level detail or logic. How can you accommodate complex program structures like iteration? This is the area where software gets really tricky. Fortunately, inverts are easily extended to handle such things as sets, subsets, random variables, and database interactions. They do so in a way that completely removes the need to specify the underlying logic. We will provide more details on this later. Invert structures can be constructed and viewed in a special software tool that we call the Invert Builder. Here you can see the desktop where you can assemble invert structures. To the left are the libraries where the various inverts are organised. Won't all of this fill the screen? You can imagine an invert structure can quickly get big. However, a software program would be represented using dozens of scrollable tabbed panels where invert structures can easily be organised and displayed. It's rare that you would ever need to look more than 6 or 7 levels deep on anything. When you do, you would typically be going 6 or 7 levels deep on that item only, not on everything. We're now going to briefly touch on 3 of the most complex and confusing types of constructs: numerical structures, sets, and random variables. Programmers think of these as all being fundamentally similar, arrays of numbers that you need to loop through. These loops illustrate what makes software programming so difficult, And since the pseudocode tends to follow the logic of the software, it also contains many loops, often going many levels deep. In the software program of 100,000 lines or more, the looping and branching logic can quickly form a huge, tangled mess. Because of this, it might seem hard to imagine that you'd be able to represent them cleanly and simply without getting bogged down with implementation details. But in fact, we can represent them using just a few small tweaks to our standard invert mechanism. The key to it is to start thinking in terms of what they are and not how to process them. Starting to sound familiar? We want to focus here on whether something is a singleton or a set. It's not quite as simple as it seems. Let's take a closer look. We'll start with numerical structures. Here are some simple examples. We mentioned earlier having over 150 inverts that allow you to specify one structure in terms of another structure. Even though numerical structures can contain many numbers, they are actually all singletons. You can easily see this in the way we specify the sum of two arrays. We refer here to the arrays themselves and not their individual elements. Numerical structures form a kind of hierarchy. A number can be viewed as an array with a single element. Likewise, an array can be viewed as a table with a single column or row. This allows you to easily combine different numerical structures by simply substituting in something of a lower dimension. Obviously, we have special controls to make sure that this is done properly. This can be very useful when dealing with mathematical constructs. For example, here's an array that is specified using a ratio in which each attribute represents an array. In this example, each array element in the numerator is divided by the corresponding array element in the denominator, giving an array 2, 2, 2, 4. In the second case, each element in the numerator is divided by 2, giving an array 1, 2, 3, 4. Let's now turn to sets. You'll recall that in the statistical summaries we showed earlier that a set was indicated using a double border. Of course. In the same way that you can have sets of numbers, you can also have sets of arrays, sets of tables, and so on. There are many different types of sets. The set might originate somewhere, such as in a file or database, or it might be derived from another set, perhaps as some kind of subset or sort. Sets need to have special coordination controls when they're being combined with other sets. Rest assured, we handle all of this in an elegant way that requires no logical thinking from you. This is a rich topic that is beyond the scope of this video. We plan to produce further videos on this and other advanced topics. Now let's look at random variables. A random variable is a strange hybrid. In some situations it behaves like a singleton, but in others like a set, since we may be interested in the set of values that it can take. Thus, it needs special treatment. The actuator supports a rich variety of these random variables. Each one can be based on one of dozens of different probability distributions. In addition, it can represent any kind of numerical structure, whether a singleton or a set. Not only that, but all of these can be combined with non-random numerical structures, sets, and correlations. And yes, you've guessed it, no logic is needed. Random variables can be used in a variety of models, including Monte Carlo simulation, longitudinal models, such as for queuing theory and epidemiology, and stochastic within stochastic, for example when modelling financial derivatives. The actuator handles all of these. Also worth noting is that in many other sophisticated concepts, such as yield curves and projected cash flow streams, can be built from these kind of random structures. The possibilities here are truly vast. And one final thing. Every single numerical element can easily be rounded, whether it's a single number or some kind of array or table, or perhaps a set of arrays or tables, even random sets of structures. Here you can see the different kinds of rounding that's available. As you can see by now, this is a vast topic, and we've only had time to scratch the surface for you here. In the future, we hope to put out some more detailed videos. You can also find further information on our website, Ac28R.com. Incidentally, you might be wondering how you can improve on all of this. The answer is that you can't. So far, we've not found any limit to what the actuator can do. The inverts are flexible and can be combined in limitless ways. So every single element that you might want to customize, you can customize. Because the inverts are visual and don't need logic, they're easier to use than you could have ever dreamed. There is nothing missing and nothing superfluous. We made some strong claims in the first video. Let's just quickly check on how well they've held up so far. No more vague and confusing specifications. Our inverts are visual, easy to use, and easy to understand. Compare this to pseudocode that is dense with logic and hard to wade through. Compare this also to large language AI models that rely on human input that can never be sufficiently precise. They are complete down to the tiniest detail. Our inverts cover every element, all the way down to the rounding. You'll recall that MIT and Intel said that this cannot be done with pseudocode. And LLMs are not designed for detailed input. No more never-ending processes. Invert structures can quickly be built by a non-techie. Everyone shares a common understanding of what they did. This leads to easier project management and fewer meetings. So what are the implications of all of this? You know exactly what your software application is supposed to do, and you don't need a degree in engineering. The invert specifications also serve as your documentation, and they always stay up to date. And modifications are quick and easy to make. So pretty good so far? In our third and final video, you will see the actuator in action, the computer that writes its own code. You will see how it can take these invert structures, analyze them, and in no time at all, it generates precise, bulletproof code that it then executes, right in front of your eyes.